This meeting is being recorded.
Good afternoon and welcome everybody, and particularly our today's speaker, Dr. Maciej Zgirski from our institute, who will be presenting his results on nanoscale thermodynamics. Please go on.
Okay, thank you very much for giving opportunity. Good morning, ladies and gentlemen. It's nice to see many familiar faces on the other side of the screen. Among of you, there are many my friends and also many my previous and current collaborators. So thank you for joining me today. I will talk about fast time resolved thermometry. So this is the method developed in my lab, a pioneering method of measuring thermal transients with nanosecond resolution. My field of studies is thermodynamics at nanoscale. So in the next few minutes, you will get to know how to extract temperature of the nanoscale system by measuring somewhat abstract probability. And so my presentation will focus mainly on the set of 5 publications comprising the basis for my habilitation, because this seminar is devoted to my habilitation mainly. But in the second part, I will talk also about some new unpublished data which show perspectives of the switching thermometry of this new novel method that I'm developing. So first, to give you a motivation for my studies, let's consider a simple system in which you have the small body of heat capacity CV, which is thermally coupled with bigger reservoir. If we keep this body at elevated temperature dT above the reservoir temperature, then we can expect that there is some energy flowing between these bodies, and the rate of the internal energy of the body is proportional to departure of the temperature from the equilibrium. So this kind of equation was first, as I remember, written down by Newton. So this is cooling equation. Basically, if we solve this equation, we see it is exponential in linear regime with decay time tau, which is ratio of the heat capacity of the body divided by its conductance, thermal conductance to reservoir. If we now consider such times in nanoscale, you can easily find that as you approach millikelvin temperature, a few tenths of milliK, the relaxation time of electrons can be easily as large as 10, 100 microseconds. But as you go towards 1K, if you rise this temperature, still you are very low, but you rise this temperature, these processes of equilibration at nanoscale become much faster. So you can easily arrive to a situation in which your electrons relax with characteristic time of 10 nanoseconds at 1K. So here, this gives roughly this 10 nanoseconds to 10 microseconds. This gives you the time span of the thermal processes which are at nanoscale. So to be able to trace such fast processes, you need a tool which would be able which would be sufficiently fast to see the variation, to changes. So some time ago, it was noticed by famous physicist Andrew Cleland, very well known in nanoscale community of superconducting devices, that thermodynamic studies are far behind corresponding electrical and magnetic investigations. So electrical and magnetic research is common, but thermodynamical experimental thermodynamics is not so common, and this dearth he attributed to lack of fast and robust thermometer that could be easily integrated with nanoscale structures. So possessing such thermometer, we could measure the various fundamental processes at nanoscale. We could get the direct insight into such processes. So here in this slide, I would like to show you what kind of processes I'm talking about, what kind of processes, microscopic processes we can consider. So you know that at low temperatures, electrons are thermally decoupled from phonons, so they have their own temperature, which can be quite elevated above phonon temperature. And they can rise this temperature by absorbing photons. They can also emit photons. Emission of photons is it is black body radiation. They can lower their energy by diffusing to regions of lower temperature. This is hot electron diffusion. They can give up the excess energy to phonons in the process which is known as electron-phonon coupling. Finally, phonons in the nanostructure, they can relax by emitting phonons to the substrates. Here, Kapitsa resistance plays a role. And phonons in substrate can redistribute energy along the substrate over quite large distances by substrate. The substrate phonons can redistribute this energy. So this kind of fundamental processes has been investigated so far mainly in steady states. So researchers, they heated one part of the nanostructure and they measured the temperature in some remote place. They measured temperature gradient, and then by assumption of certain thermal models, they could extract dynamical thermal parameters of the system, like thermal relaxation time, or they could get insight into dynamics, but not directly. So I would like to have different approach. I want to measure this rapid variation directly. So as I showed you before, for this I need a tool which would be sufficiently fast. And then I can extract this time, I can get experimental insight without, which would be independent of the model assumed. So instead of calculating the relaxation time by measuring some steady state response, I could get the direct access. Okay, so a part of such fundamental processes, when we talk about fast thermometry, we immediately have in mind calorimetry, which is aimed at measuring the heat associated with cooling or heating up of the nanostructure. This is also involves measurement of the heat associated with phase transition. We have calorimetry. Calorimetry is the basic building block for bolometry. So bolometry deals with detection of radiation. Finally, we must remember that this is often overlooked, but we need to understand properly the thermal budget of various nanoscale devices in order for these devices to work properly. Here we can talk about qubits, about devices based on qubits, quantum bits, about microcoolers, and also about rapid single flux quantum devices, which are becoming more and more popular also in neuromorphic computing. So my claim is that if you want to, at this very low temperature, it's very easy to overheat due to some dissipation which is intrinsically involved in the operation of the device. You can easily overheat the device, and if you neglect the thermal effects, your device may not work properly. So my thermometry could provide a diagnostic tool for better understanding of the thermal effects in such devices. When we talk about thermometry, we also, more generally, if we assume that temperature is not well-defined quantity in some highly non-equilibrium processes, we can still talk about quasiparticle propagation. So such quasiparticles, we know that they spoil metrological application of many nanoscale devices like single electron boxes, but or also reduce the coherence time of qubits, but can be used to our advantage. For example, if we talk about bolometers. So bolometer detects the incident radiation only because this photon creates some quasiparticle in superconducting bolometer. So also my method which I will describe will help us to understand this quasiparticle propagation, quasiparticle dynamics. And there is new emerging field of quantum thermodynamics, which deals with the heat transfers associated with the exchange of single particles. This can be single electrons, this can be single photons, but this can be also single vortices of magnetic field. So we can talk about thermal effects arising, for example, from manipulating of the single vortex. So this is some general broad picture which I wanted you to display for you, so that to give the motivation and to show importance of the thermometry of nanoscale. Now it's time to introduce the main hero of today's talk, my very good friend, which is superconducting bridge, aluminum superconducting bridge, obtained with e-beam lithography. This is polycrystalline aluminum with constriction 60 nanometer in the middle. It is type of the Josephson junction. So usually when we think about Josephson junction, we mean tunnel junction, which means that we have many transmission channels, each with very small transmission. But this type of structure is also Josephson junction. It contains, it is diffusive link. It contains many transmission channels, and we have all the distribution, all possible transmissions here are involved. And the advantage of this structure over the tunnel junction is that it is very robust. It is easy to fabricate. It shows good thermal sensitivity. And also tunnel junction also shows, but this one also, using this device, we can work with higher currents, which is also more convenient from experimental or purely technical point of view. So this is my thermometer. When we now measure IV curve of such current voltage characteristic of such bridge, we'll find at the lowest temperatures pronounced supercurrent branch, meaning that there is current flows in such bridge. This is superconducting bridge with no drop of voltage. But upon exceeding a certain threshold, the junction switches to the normal state, and it is normal state. It's the temperature of the bridge in this state is much above TC because it is strongly overheated. It is due to self-heating. And now if we increase temperature, you see that this supercurrent branch becomes smaller. So already this behavior gives you an idea that it could be perhaps employed as a device for sensing temperature, because it shows the critical current or switching current, the one at which junction switches from superconducting state to normal state, shows pronounced sensitivity to the changes in temperature. So now I will tell you what I do to measure this switching current accurately. So I want to define well the value at which junction switches from superconducting to normal state. For this, I use switching protocol, switching measurements. I send on the junction, say, 10,000 pulses, this capital N, and in response to each pulse, junction may switch, but it doesn't need to switch. If I send amplitude of if amplitude of the pulse is too low, in response to all pulses, junction doesn't switch because simply the current is too low. Then if it is too high, in response to all current pulses, junction switches. Then we tell that the probability of switching is 1. But in between, we have some non-trivial region when junction may switch, but it doesn't need to switch. So it's switching is stochastic, it's probabilistic, it's characterized by the switching probability, which is given by the number of times junctions switched to the total number we tried to switch the junction. So this experiment remains in full analogy with the familiar experiment in which you toss a coin to determine the probability of obtaining head or tail. But I can unlike with fair coin, here I can tune the switching probability by adjusting the current amplitude. So this is basically the switching protocol. So here I define the basic measurable quantity, which is the most important quantity in my measurements. So I derive all other properties of the physical system by measuring this probability, by measuring probability of the switching process. Okay, and now if we look at this kind of curve, okay, some more introduction. This kind of curve, for its shape, is known as an S curve. It reminds the letter of S, yes. And now the point is that if we measure these S curves at different temperatures, here you see I measured these S curves from 400 milli-K to above 800 milli-K with step of 5 milli-K. These are experimental data. So you see that each time I increase 5 milli-K, temperature by 5 milli-K, the S curve is shifted towards lower testing current values. So from this already you see that for example, if I test my junction with pulses of amplitude 50 microamps, and say I am here at 600 milli-K. Okay, so let's test with some this value, and I have probability of 0.3. Then by increasing the temperature by 5 milli-K, I increase probability by roughly 0.1, 0.2. Yes, this is in principle this vertical cut here. So you see that for different temperature, I have different probability. And this gives already, it shows that we have really nice temperature sensitivity, and we can use probability as a sensitive probe, switching probability as a sensitive probe for the temperature. Okay, so here you see what I did in the left panel. I measured the switching probability for fixed values of the temperature. So I measured the probability corresponding to 390 milli-K. Then I increased the temperature by 2 milli-K. This is the global bath temperature of the fridge. I measure again this probability and again and again. And this gives me the simplest calibration curve. So this kind of curves are very reproducible. Here you see that, okay, I have quite good control over the stabilization of the temperature, and this probability is really nicely determined. Now, when I measure such thermal S-curves, so temperature dependencies of probability at various temperatures. So if I measure slopes here at various temperatures, I can build out my temperature, the curve which shows me what is the temperature sensitivity at given temperatures. Yes. So in principle, here is in the right panel, I plotted the inverse responsivity. So responsivity tells you how much probability changes in response to unit change in temperature. So you see that since it is inverse, then we see that the highest responsivity is at higher temperatures. So this can be treated as a calibration curve. Okay, and this is one direct method of extracting temperature from this switching probability. You can treat it this as a calibration curve, but we can also measure the critical current of the junction as a function of temperature. And you will find now that the measured quantity will be the switching current corresponding to switching probability equal half. And this type of calibration curve can be understood in terms of Ambegaocar-Baratov theory, which is very well known in the physics of tunnel junctions, when we have many channels, each with vanishingly small probability. But it turns out that for the diffusive bridge, which consists of the not so highly transmitting channels, but okay, that with transmission, with average transmission, say at the level of 0.6, 0.7, if you plug in the numbers, it turns out that then the dependence is actually very, very close to the one expected for the tunnel junction. So here I imposed actually, it's not even a fit, it is, okay, the only fitted parameter is what is known in tunnel junction, this tunnel resistance, but here it is just the resistance of the bridge. If you impose on the bridge, you get properly the temperature dependence. Okay, so now we have basically two methods of the measuring temperature. One is we measure the switching current, and this uniquely gives us temperature, and another is we measure probability at a fixed testing current, and this also gives us the temperature. Okay, so I will now, so far I have been talking only about principle of the static thermometry, but now I would like to add some dynamic feature. So this dynamic feature is the idea taken from the laser physics, where you use pump and probe protocol. So you send the heating pulse, you energize some part of your nanostructure, your heater, and then some time later, which is known here as a delay time, you test your junction with short pulse. This tau means that the duration, typically in my experiments, is 5 to 10 nanoseconds. And this, in fact, sets the resolution of your method. So the duration of this pulse tells you that the resolution of the method. And now by applying many such sequences, 10,000, you pump and probe, you can measure the probability corresponding to a given delay after that heating pulse was sent. So let's look how it works in practice. So here, first experiment is the thermal relaxation of a superconducting wire. So what we have just simple bridge, constriction in the superconducting wire, and we switch this bridge, it goes above TC, and now it cools down. And as it cools down, we probe it with this pump and probe protocol, and we see as the time progresses, we see progressive relaxation of the switching current back to its initial value. So for first 20 nanoseconds, we cannot measure after the bridge was switched because it is still above TC, but as soon as it transits back to the superconducting state, the switching protocol is valid, and we can measure this relaxation of the switching current. Now, using the calibration curve, I mean, associating switching current with temperature, we can recalculate this trace into temporal trace of the temperature. And okay, and this curve, these triangles, they show that the relaxation profile of the electron temperature in superconducting nanowire. So this can be used as considered as a proof of concept experiment. Here with this thick red line, I applied a theory taking into account electron phonon coupling and electron diffusion. So it captures quite well the behavior, the decay time. Okay, so we can, in principle, we can repeat this experiment at various temperatures. So we can measure at small, let's focus on this left panel first. So we can measure the temperature at small departures from the equilibrium. Then we expect that the relaxing electrons their temperatures should relax exponentially. So this is what you see here. You have a logarithmic scale and straight lines indicating exponential decay of the temperature. But this method, temperature from probability, is applicable for linear processes. So when there are small departures from the equilibrium from the above temperatures. If we consider big departures, if we are in nonlinear regime, then this second method, which is less sensitive but allows you to capture all the dynamics. So it allows you to really trace from just below TC down to the above temperature. So these are these two things. And now, okay, taking the exponent, this decay time in linear regime, we can plot the relaxation time of electrons as a function of temperature. So here, these curves okay, here this bunch of curves, these are my experimental data. So you see that I can measure the relaxation times as soon as the bridge becomes sensitive to temperature, which is for this bridge, okay, for aluminum bridge is roughly 300 milli-K. And here we see that the relaxation profiles for the nanowires of various lengths, from 30 micrometers to 800 micrometers. So you see that 800 micrometers relaxes slower, at slower pace than the shorter wires. And this is perhaps due to hot electron diffusion playing a role. But at the higher temperatures, they all, we may say that, okay, all of them, they show very similar relaxation time. And here, the relaxation is dominated above 0.6 by electron-phonon coupling. I plotted here with the solid thick line, orange line, I plotted the analytical prediction of electron-phonon coupling theory. And we see that the agreement at the lowest, at the highest temperatures is very good, but then at the lower temperatures we get the measured times are lower, and this can be due to the fact that the hot electron diffusion should be taken into account in addition. But even if we take this into account, still the discrepancy remains. For comparison, I added here this data measured at the lowest temperatures. These are data from literature. So you see that people were able to measure the relaxation times down to, say, okay, 10, 20 microseconds. And then they couldn't continue because simply their method was too slow. So I can measure this much faster relaxation times. And there is, of course, here the question. Okay, here we have theory, here the existing experimental data, and here I measure actually faster relaxation times than measured with these other methods. Okay, so now I have been talking mainly about this proof of concept experiment. So now I would like to show you some maybe the best experiment that I have done for my habilitation. This is focused on direct detection of hot electron diffusion, direct monitoring of the quasiparticles moving in the superconducting nanowires. So now we are considering this electron relaxation channel. So, okay, diffusion. Let's consider such example. We have heater, copper heater. It is also, some photo of it is displayed on the left. We have bridge here placed 60 micrometers away from the heater, and we hit the bridge with fast pulse, 5 nanoseconds. We create population of quasiparticles. They diffuse through this bottleneck to the wire, and then they propagate along the wire. So if we think about this process in terms of the free particle diffusion, we expect that at this point, at the point of injection, the quasiparticle population should be reduced exponentially. But here at the site, we need some time for electrons to arrive to the bridge. So first we expect no signal, then signal should pick up and should go down, should relax back to the equilibrium. So in principle, we expect that within free particle model that this should be the evolution of the Gaussian profile. So what our experiment tells us about this process? So first, zero time corresponds to coincidence of the heating and then the probing pulse. So this is heating pulse sent on the heater, and this is the testing pulse. So when they coincide, they crosstalk. we have crosstalk, so that is why we have some high signal. This the signal of the crosstalk changes when we change the polarity of the heating pulse. Then after the heating pulse is over, we see no signal at the detector still. So it's the detector is silent for 30-40 nanoseconds. And then the signal goes up, it achieves maximum at 300 nanoseconds, and then it goes down. So as predicted as you would predict it in theory. So here you see the diffusive profile of the quasiparticles. Okay, so what is important that when we invert polarity, you see that crosstalk changes, but the thermal effect stays the same, meaning that this is really okay thermal effect. So we don't have, it is not ringing, it is it is not, the signal is not sensitive here on the polarity of the used pulse. We can recalculate this trace into temperature by using the calibration curve. So you will see here that we have here many such diffusive profiles measured at different temperatures. So as we increase temperature, the diffusive profiles becomes smaller and smaller, and this is due to the fact that electrons diffusing towards the detector are annihilated on the way. They emit phonons, and electron-phonon coupling is more pronounced at higher temperatures. So we expect that at higher temperatures, the quasiparticles should be annihilated more efficiently, so they don't arrive to detector. Here, I imposed these solid lines are predictions of the solution of the one-dimensional heat flow equation, taking into account hot electron diffusion, electron-photon coupling, and also having some bias term delivering this, injecting these particles. So, okay, here you see that the signal picks up at 300 nanoseconds. So it is in good agreement if we consider Einstein-Smoluchowski law, and we take this time of the arrival and the distance between the emitter and detector, which is 60 micrometers. We find that we expect that the maximum actually should be after 280 nanoseconds. We observe it here after maybe 300 nanoseconds. So we see that it is in good agreement. So the process we observe, it is the really direct observation of hot electron diffusion. If we measure these profiles at still higher temperatures, we can see here at 800 milli-K, we can measure the departure from the base value of temperature only equal 400 microkelvin with blur at the level of 100 microkelvin. So it shows that method is not only very, gives only not only very good temporal resolution, but also it gives very good vertical resolution, very good temperature resolution. Okay. So here are some figures of merit, responsivity, and noise equivalent temperature, which are often used as metrics for the thermometry. This is in left panel you have responsivity, so it tells you how much the probability changes in the response to the unit temperature change. Having the responsivity, we can calculate what is noise equivalent temperature, which is the smallest resolvable temperature we can distinguish in our experiment. But to do this, we need to know actually the accuracy of determining the probability. And to find this accuracy, we need to call this, again, this analogy of the 2000 coin. So imagine you toss a coin 10,000 times. So I send 10,000 pulses on my junction. This is like tossing 10,000 times a coin. We count number of heads and we get, say, 5,150. Then we repeat again. And this time we get 4,850. We repeat again. So each time we repeat this experiment, we get slightly different number, but the average value is the same. And the actual number that we obtain is governed by binomial distribution. So what I did here with this with this experimental red data, I repeated the experiment of sending 10,000 pulses on my junction many times. And then after each train, I recorded the number of times junction switched, and then I repeated the experiment, and doing so, I could build histogram. And this histogram remains in agreement with what is expected from binomial distribution. And you see that for 10,000 pulses, okay, we expect that the broadening of this histogram is at the level of 50. So this can be treated as an accuracy of measuring probability. I used to tell about it, to think about it as this is kind of statistical noise. This is not electromagnetic noise, but this is noise arising from the purely statistical nature of the probing of the system. So now when we plug back this accuracy of determining the probability to the formula for noise equivalent temperature, we can see, okay, we will get, okay, this blue curve, but now the proper axis is on the right. So what is the meaning of this noise equivalent temperature? Say if it is 10 millikelvin per square root n, like at the highest temperature, with n equal 10,000 pulses, it gives us uncertainty of the temperature determination 100 microkelvin. So, and this is also what you expect, what I showed you already directly here in this lowest curve, where we have 100 microkelvin accuracy of determining the temperature, the highest temperature. Okay. So what is interesting here, that usually when we talk about devices, we talk about this noise equivalent temperatures. We tell about some accuracy per square root hertz, but here it is per square root of n. But the increasing number of probing pulses has the effect of extending the experiment. So this plays a role as you have in normal experiment, as you average out some high frequency components, and by doing so you can increase the accuracy. Okay, so we have in our experiment two relaxation. Okay, the method is not only, the switching thermometer is not only applicable for measuring fast processes. We can also use it to measure processes which are relatively slow. So say we energize our bridge with one pulse, then we see the electrons relaxing back to equilibrium. It takes for them roughly 1 microsecond here, these blue dots. But if we send many pulses, which are sufficiently densely packed, we see that our relaxation curves consist of two exponential decays. One is fast, with the same relaxation time as the first one. But the second is much slower, 1,000 times smaller. So it turns out that this first time is the relaxation time associated with the time this is the time that electrons need to relax with phonons. And the much longer time, this above 1 millisecond, is time for relaxing local phonons with the buff. So we can design in this experiment, we can see the separation of these two times. One is fast, one is slow. Also in this right panel, you can see that as we here, I plotted the phonon temperature measured as a function of the number of heating pulses which are sent in a row. So after each heating pulse, which switches the junction, we hit slightly phonons. And as we keep increasing of number of pulses, the phonons becomes overheated even by 80 milli-K. So it is important to remember this effect, very often forgotten, that phonons are usually treated as a reservoir. But this experiment is designed to show that it is actually, you can overheat them. So having these two relaxation times with so different relaxation constant, we can build correlation. What we want now, what we need to remember, we know that switching event rises the temperature. This is because it is dissipative, it drives the junction above TC. And also we know that the switching probability increases with temperature. So if we send pulses which are, when the period of testing pulses is shorter than the thermal relaxation time, then we expect correlation, because then the next testing is influenced by the result of the previous testing. If we obtain switching in the previous pulse, then of course the probability for next switching is enhanced. So here is the scope trace of the switching events in correlated regime. You see that the switching pulses, the switching events, they appear in bunches. So for example, here we have 7 switching events in a row, here 4, 2, 1, 4. So when we switched once, it's increased probability to switch in next pulses. And this is because of the internal heating in the junction. So now in this correlated regime, if we measure the S-curve, okay, here we have one S-curve. This black one is the S-curve measure for independent pulses. So when period is sufficiently big, then the pulses do not interact with each other. After each pulse, we allow system to equilibrate back to the above temperature. So we have familiar S-curve. But if we send them one by one and we don't allow after each switching to relax, we, instead of this, we see some abrupt behavior. So we can measure the point at which some small fraction of pulses switches. So in this point, in this green triangle, we have basically the scenario as presented here. We have a pattern of rare bunches. But then if we want to increase slightly this number of switched pulses, we can't do it actually, because then the system immediately decides to end up in the state when all pulses are switched. Okay, and now let's focus. And it turns out that this point here, this last point at which system exists in the low switching state, is metastable one. So if we keep measuring this point, each point corresponds here to sending 10,000 pulses on the junction. We see that the fraction of the switched pulses oscillates around some mean value, but then spontaneously after some time, the system switches to the transits to a new state in which all pulses lead to testing pulses lead to switching. So these pulses here, down there, they correspond to the setting, to this kind of pattern of rare switching events with bunches. And here you would see on scope that your screen would be fully packed with the switching events. So I did to predict this behavior, or not to predict, to explain this behavior, I developed model. This is a recursive model which relates the temperature in the next testing pulse to the temperature in the previous testing pulse. So n numbers the testing pulses. And the model involves stochastic heating due to stochastic nature of switching, stochastic heating of electrons and phonons, and deterministic cooling of phonons. So then this model can be combined with each temperature uniquely gives a switching probability at any particular moment of the experiment. So each TE is related to probability. This is experimental curve, so you can treat it as a kind of calibration curve from which you can read what is the switching probability corresponding to given temperature. If you apply this model to iterate this model for n equal 1, 2, 3, 4, and so on, you will find here now, we can look at the lowest panel with these green dots. You will find that the switching probability takes on a random character. So it changes, switching probability for each pulse changes randomly, jumping between two branches. And after some time, okay, switching probability goes to 1, and then this is the moment also when electron temperature goes to 600 millik. So electrons are overheated in this state at the moment of the testing by 600 millik. So what is important that this is really metastable state, both in simulation and in experiment. If I repeat this experiment, this simulation, this kind of global transition may happen in various moments. So this is the process with tunable lifetime. So I can, by adjusting the distance between pulses, by changing current, temperature of magnetic field, I can change the lifetime of this metastable state. So I created artificial process, which quite interestingly remains in kind of analogy to familiar process of the multi-phase sleep escape known from superconducting wires, where also the many phase slips must produce sufficient correlation, which leads to the final switching of the wire to the normal state due to unlikely overheating. So this kind of okay, this is for people familiar with phase slips and with 1D superconductivity. More on this can be found, of course, in this paper, which is also presented in habilitation. Okay, so this is important thing. Some people, they would say, okay, you measure temperature very fast. Are you really measuring the temperature? Maybe you measure okay, your temperature is not properly defined quantity because thermodynamic temperature requires that there are well-defined distribution of electrons. Electrons should be described with Fermi-Dirac distribution. The distribution of quasiparticles should follow Fermi-Dirac distribution. So are you sure that you have the proper distribution? Maybe you measure some, maybe rather you should call this temperature some effective dynamic temperature. So here is the answer. We have again the diffusive profile, which I showed you already. Now what we can do, we can measure S-curves at point A, B, C, D, E, F, G. And these S-curves, I call them dynamic S-curves because they are measured just after a fixed delay after the heating pulse was launched. And then we measure the S-curve, the probability, the switching, the testing current dependence of the switching probability after this fixed time. We can also measure S-curves at some static temperature. And now we can impose the dynamic and static S-curve. And it turns out that for each S-curve, dynamic S-curve found, we can find its mate in the family of static S-curves. So this is here displayed on the right, in these right panels. So as long as we assume that the switching behavior, switching probability is a fingerprint of the electron quasiparticle distribution, I assume that we can consider that since we have coincidence of the static and dynamic S-curves, that we can assume that our temperature is measured in this experiment during thermal transients is well-defined thermodynamic quantity. Okay. So I have hopefully 5 more minutes or some time. Okay, so I would like to show you, this was basically what I presented in my habilitation, but I would like to show you also that I'm still very active and I'm developing these ideas. So switching measurements are not only good for detecting temperature, they are perfect, it turns out, for investigating superconducting vortices. So here we have the layout of the sample. This is here this same photo of the sample, which was made here in my lab. So you see here we have the superconducting nanowire with constriction and box. This box may accept superconducting vortices when in some finite magnetic field. And then it turns out that the superconducting, the switching current, critical current of the bridge is sensitive to the presence of the vortices in this box. So if we can sense these vortices, if we can push them here, manipulate, then I would say that this is a very simple device which belongs to the field of vortex electronics. So this involves monitoring and manipulation of vortices with electric current and magnetic field. So let's see at the trace. So we have here such double box structure. You see, this is the switching current dependence on magnetic field. You see that this for small field, the sample shows the Meissner screening behavior. So we have screening currents which push away the magnetic field. But upon exceeding a certain threshold, we allow one vortex enter to one box and another to another box. By the way, these panels on the right are Ginzburg-Landau simulation of this structure provided by Michał Wyszyński from University of Antwerp, with whom I have collaboration. And then still when we increase, so this sharp transition corresponds to the onset of the one vortex into box. Here, 2 vortices, here 3 vortices. So the scheme of the switching current is very sensitive to the presence of vortices. And moreover, this is not, I don't have the time to show it, but we can also push away these vortices with the current, and we can change the threshold for the switching. So this gives us a logical component in our studies. Okay. I would like to shortly show you another experiment also that currently I'm doing. This is quasiparticle annihilation. So the structure is following. Here we have heater. Here we have thermometer. Here we have big box, 400 by 400 micrometers. And this box is full of in certain magnetic field, it can accept here superconducting vortices. And now the point is simple. We send here the heating pulse. We switch this wire, we emit quasiparticles for here, and they diffuse towards the thermometer. And we want to, we ask following questions. Are vortices able to influence the flux of quasiparticles diffusing to the thermometer? So here is the answer. Here, the black curve, the biggest one, the biggest amplitude corresponds to the signal of this is diffusive profile of quasiparticles at thermometer with 0 magnetic field. But as we increase magnetic field, you see that then the increase of temperature at the thermometer becomes smaller and smaller, and it actually quickly saturates. It already half millitesla is enough almost to obtain the optimum. So this shows that the quasiparticles diffusing in this square, which is full of vortices now, can be annihilated on the way. So vortices, they act as a quasiparticle traps. We can also make the same study for the same structure in steady states. So in this panel on the right, you see that with magnetic field equals 0, we see that the suppression of the switching current is the biggest. Suppression of the current means that there is the biggest flux of quasiparticle arriving. So the more quasiparticles at the junction, the bigger suppression. If there is smaller suppression, it means that we have less quasiparticles. So they disappeared, although heating was the same. So it shows that already in steady states, we see that vortices quite nicely, they are able to annihilate quasiparticles. Okay, now question, can we see a single vortex? Okay, so now our sample is here, we heat, we will provide diffusion of quasiparticles, but now we don't have many vortices, but just one. can this one vortex annihilate quasiparticles on the way? Okay, and then those who are able to pass the vortex are able to continue, and then they are detected here at the detector. So distance between detector and vortex box is 30 micrometers, and between vortex box and the heater also 30 micrometers. So here is the structure. Okay, structures, the previous and this one were prepared by Jonas Peltonen from Aalto University. So here you see the heater. Here you have vortex box, and here you have the detector, thermometer. Okay, so now if we measure at zero magnetic field, if we measure with no heating, we see just this black profile, which shows the characteristic of our detector in magnetic field. So it shows the switching current dependence of the detector as a function of magnetic field, no any features visible. But now we introduce heating, and we measure the same profile, but at some time when we know that quasiparticles should be arriving to detector. So what we see that at the places where we expect the first or second vortex entry, we see small enhancement. Here it is given with the zoom. We see enhancement of the switching current. So enhancement of the switching current again means that there is less quasiparticles arriving, because quasiparticles, more of them, they will lower the order parameter. So less of them arriving means higher switching current, which means that indeed this one vortex provided we were able to sense the presence of the one vortex between heater and detector by the influence it exerts on the flux of diffusing quasiparticles. So this is detection. Single vortex absorbs quasiparticles and can be visible, although it is 30 micrometers away from detector, okay? Okay, and this would be the last thing, very quickly, just to give me 2 minutes. This is phonon. Also, another process is which we can study with switching thermometry. We have 2 nanostructures which are galvanically disconnected, but one structure can be heated and it can emit phonons to the substrate, and these phonons can go along the substrate and they can excite phonons in another nanostructure, and these phonons, they can excite electrons in another nanostructure. So this type of structure, say we have this type here is generic shape of the sample. We have heating line, and here we have a couple of junctions. And now here schematically I draw the phonons. They can be ballistic, diffusive, bulk, surface. We don't know exactly, but by means of these phonons, we can redistribute energy between these non-galvanically connected lines. And here is the actual sample that we have. So we have copper heating line, and here we have line with thermometer in the middle. And what we see here is the base of the signal. Then we have some crosstalk due to coincidence of the heating pulse and the testing pulse. Then we see some enhancement of the signal, immediate enhancement after heating, which perhaps corresponds to some surface phonons, which are immediately visible by the second structure. But then after roughly 120 nanoseconds, we see the abrupt change in the signal. And this abrupt change and the time delay, which we have here, 120 nanoseconds, corresponds to the time which we expect for acoustic wave traveling distance from the nanostructures to the bottom of the surface of the bottom surface of the substrates and back to the structure. So we have now our assumption is that this is perhaps here we see effect of ballistic phonons. These are surface phonons. Okay. Yes, this is just to mention that all experiments that I presented to you were only possible because I built my lab from the scratch. It took me a lot of time. Maybe also this is the reason why my habilitation is a bit delayed, because I'm becoming quite old guy. but I have to build everything from the scratch. So I have dilution refrigerator, I have helium 3 sorption fridge. So I have 2 experimental devices to perform low temperature measurements. I designed and built for them the sample holders, wiring. Also, I wrote review programs because these are very automated. I mean, without automation, it would be difficult actually to perform these switching measurements. And I also bought and customized and took part in design on the E-beam gun evaporator, which is important for to have samples. So it took me a lot of time. So this is something that should be, I think, appreciated in my habilitation, but because this is prerequisite to do any experimental work. Okay. Over years, I received funding from Foundation for Polish Science. So currently, I'm running grant. It is coming to an end. First team. So together, I gathered 3.2 million zlotys in this grant. Another my currently running grant is Sonata Bis, 3.4 million zlotys, and I took part. My previous project was Homing Plus, where I was also leader, and I took part as one of the authors of the grant application in our institute grant, famous Eagle, which allowed me to buy this low temperature apparatus. Okay, so in summary, I can monitor fast thermal transients in time domain with switching thermometry. So I showed you nanosecond resolution, also very good accuracy, vertical accuracy, temperature accuracy. This is 2 orders of magnitude improvement over the state art of mesoscopic thermometry. It is applicable to all Josephson junctions that exhibit hysteresis. I also showed you that there is potential for detecting vortices and studies of substrate phonons. I would like to thank my friends who are working with me, Marek and Konrad, on daily basis. Marek is my close collaborator who is running with me all experiments. Konrad is my PhD student, also very nice guy who is already with me 5 years. He's going to defend next year. And Alexander Savin from Low Temperature Laboratory is my friend and advisor in scientific and technical advisor, so I can always rely on him when I have some questions. He's very experienced in low temperature measurements. So this is, I would say, core of my team. Yes, thank you very much. And here are relevant publications which comprise the basis for my habilitation. Thank you. Sorry for talking slightly too long. I wanted to show this additional data so that you get the feeling that also this switching thermometer is really rapidly developing in my lab, and I hope you enjoyed it. And okay, I please ask questions. Thank you very much.